Today's first discussion is in WSP's Tech Week event is keeping Auckland moving with machine learning. It's all about the benefits of real-time data collection, machine learning and network optimization, real applications used here in New Zealand across our transport network. So over to you, Sam.
Great, thanks, Chow. You should hopefully be able to see my screen. So my name's Sam, and today we'll be presenting on keeping Auckland moving with machine learning. So in particular, we're going to be talking about how we use machine learning and other data technologies to answer three main questions. How many vehicles are travelling on our roads? How do we best manage traffic on the Auckland Harbour Bridge? And what were the impacts of COVID lockdown on our traffic network? So as Chow mentioned, my name's Sam. I'm the Digital Automation Team Lead for Transport at WSP. Ravindu is a data analyst and machine learning lead at WSP and a PhD candidate at the University of Auckland. Dan's a transportation engineer at WSP and also the journey optimization team manager for ASN, who manages our motorway networks in Auckland. He's also a PhD candidate at the University of Auckland. We're part of the Data Analytics Centre at WSP. So this is a team of people with a range of expertise across statistics, computer vision, machine learning, automation, and traffic modelling and optimization. In the past, we've been mostly focused on the traffic side of things, but we're looking to expand our reach across WSP and in some new industries as well. So to get things started, we want to ask the question of how do you get to work or school? There should be a poll coming up in the chat shortly, so drop your answers in there and we'll get back to the results later in the presentation. Why do we need to collect traffic data? Why is this of interest to us? Well, we need traffic data both to understand and optimize today's road network, but also to plan for the future. So we use traffic data for things like adjusting motorway ramp timings and traffic light timings. So this keeps traffic moving smoothly on our local roads and our motorways. We use traffic data to optimize road layout, so we can identify where we might need new bus lanes or cycle lanes or additional parking, for example. We also use it for infrastructure maintenance. So by knowing how much traffic is traveling on our roads, we can plan our road maintenance operations, but also we can use this data to optimize our road closures to do other types of maintenance like bridge replacements and maintenance of other assets on the road network. Looking to the future, we need traffic data to predict changes in traffic demands. Based on these changes, we can plan infrastructure development to suit. So for example, this might be identifying needs for new tunnels or bridges. We also use this information to look at the environmental impact of our traffic network. So by knowing the number of vehicles and the types of vehicles that are travelling, we can get an idea of the carbon emissions of our road network and take steps to try and reduce those, such as perhaps developing more public transport facilities. So how do we go about collecting traffic data? Well, the poll you're hopefully answering now is one example, but some more conventional ways are shown on this slide here. So in some cases, we might do manual counting, where we send someone out into the field to physically sit there and look at the types of traffic and the amount of traffic that's passing. But we also have devices that we can install on or in our roads. For example, tube counters, which are the rubber tubes you'll see across the road from time to time. We have inductive loops, which are coils of wire that are buried under the road surface and detect vehicles travelling over. We also have weigh in motion devices, which are steel plates that can count traffic passing over, but can also weigh trucks that are passing. This helps us get an idea of the wear and tear on our roads caused by trucks and other heavy vehicles. So the previous slide, those approaches have some limitations in that they're either manual or they require devices to be installed on in our roads, which have some disruption and maintenance concerns. We have some newer technologies which are shown here, such as GPS, cellular, and Bluetooth data. So these approaches aggregate data across a range of devices, including mobile phones, cars, and GPS units, and give us a broad picture of how people are moving throughout the city. We also have more targeted approaches, for example, radar devices, which sit next to the road and use radio waves to determine the numbers and types of vehicles that are passing. But what we're focusing on today is computer vision. Computer vision uses cameras set up alongside the road to basically collect traffic data. So what is computer vision? Before we get to that, I first want to touch on artificial intelligence and machine learning. So artificial intelligence is a very broad field, and I'm sure you've heard quite a lot about it. But generally speaking, it's programming computers to perform human-like tasks. So this is using things like maths, logic, and various algorithms to do tasks that humans may otherwise do. So for example, this might be finding the shortest route from point A in a city through to point B. This is something that a person could do by measuring out the different routes and things like that, but we can also develop an AI system to do the same thing. Machine learning takes it a step further by allowing machines to learn from data and make predictions going forward. So we can show it lots of historical data, and then it can make predictions into the future. An example of this might be training a machine learning algorithm on the levels of congestion in our city. And this would allow us to not only find the shortest route between A and B, but also look at what might be the fastest route based on current and future traffic conditions. A key point about machine learning is that we don't necessarily need to tell it how the system works. So machine learning doesn't need to know what traffic is or how cars work. We just show it examples of the types of information we're looking to get out, and it can generalize across new situations. And that brings us through to computer vision. Computer vision is the application of machine learning to derive meaning from visual inputs. So it's effectively taking a machine learning system and feeding images or videos in to get predictions out the other end. For an example of computer vision, we've got a robot here named Rob. Now, Rob has been trained to take photos of animals and predict what type of animal he's looking at. So in this case, he's come across this animal, he takes a photo, this photo gets fed into a computer vision algorithm, and based on the outputs of this algorithm, Rob's able to say, I'm 90% sure that's a tiger. Now, based on this information and what he's inferred from the photo, he can then make a decision. In this case, he decides to get out of there because it might be dangerous. Rob able to do this. How does computer vision work? Computer vision and other machine learning approaches often use something called an artificial neural network, or an ANN. So neural networks are loosely based on how the human brain works and are made up of a bunch of nodes or neurons. These are grouped together into layers and connected very densely using edges. So all the neurons are connected to all other neurons effectively in the next layer, and they don't necessarily correspond to any of the outputs. We feed in some input information, for example, this picture, and at the other end, it's able to give us a prediction of what animal it thinks the input is. We train this system by giving it thousands of photos of different animals and telling it what the correct output is. And based on this, different connections in the network get strengthened or weakened, so that when we show it a picture of a tiger, different parts of the network activate, and it's able to tell us with 90% confidence that it is in fact a tiger. We have to be careful when we train these systems to avoid accidentally building in bias or error into the system based on the types of training data we show it. So for example, if we show the system a picture of a dachshund running through water, it's 50% sure that it's a dog, but it also thinks with 40% confidence it could be a duck. And perhaps this is because it's been trained on lots of photos of ducks in water, but not many photos of dogs in water. So when we showed a photo of dog in water, it gets a bit confused. So this is an example of where we have to be really careful with the training data we provide to make sure that we don't build in these errors or biases. So put another way, computer vision is an application of machine learning that trains computers to interpret and understand the visual world. So in Rob's case, Rob was trained to interpret different types of animals from photos, and based on how he's trained, he could understand that tigers might be dangerous and he should get out of there. Computer vision is a very broad field and can be applied to a wide range of applications. Some examples include industrial applications, where computer vision could be used to detect issues on production lines or to control robots. We can use it in the medical profession to analyze scan data or other medical data and find patterns and potential issues that might not be obvious to people looking at the data. It's used a lot in self-driving cars. So a good example of this would be Autopilot by Tesla, who uses computer vision extensively to detect vehicles and people and the road itself and allow this to control its cars. And finally, with my background in bridge engineering, I'm interested in infrastructure applications, where we might be able to fly a drone around a bridge, take a bunch of photos and automatically detect issues such as cracking or corrosion. Going back to traffic though, how do we use computer vision to count vehicles? This slide shows a system that was developed in WSP, and this uses both object detection and object classification, which are two kind of broad types of computer vision. So we use object detection to work out where vehicles are present within the image, and classification to tell us what type of vehicles they are, similar to Rob classifying animals. These vehicles are tracked as they move throughout the image or through the intersection, and as they pass through different regions, it tells us information about how many vehicles are passing and the types of vehicles they are. With this sort of approach, we can get even more rich information as well, such as how long people are waiting for, what lanes they're using, and how fast they're going as well. And the data can all feed into a dashboard, which allows us to make decisions about how we manage our road network. So that's been an overview of traffic data and how we use computer vision to collect certain types of traffic data. I'll now hand over to Ravindu, who will be talking about how we use traffic data in general to get a better picture of our road network. Over to you, Ravindu.
Cool, thanks. Everyone, can you hear me? Cool. Thanks, Sam. So Sam was talking about one way we can use machine learning to count traffic. What I'll be talking about is a slightly different problem, but we're essentially still counting using machine learning to estimate traffic parameters. So let's go back to basics. I can change the slide. So imagine Mary taking a trip from her home in the North Shore to work in the CBD. For that trip, she might travel 20 kilometers on the motorway. And it's not just Mary. Hundreds of thousands of people use our motorways. And everybody uses people use different modes of transport. And they can use cars, trucks, taxis, mopeds, buses. And from the poll, we can see that most people do use cars and buses. Some people walk, cycle, and there is that one person who uses a monster truck. What happens on our motorways are a collection of trips. One thing that is useful to track is if we add up all the kilometers of all the trips traveled by everybody, what is the total number of kilometers traveled? If you had to take a guess, what do you think is approximately the total number of kilometers traveled by all vehicles on our motorway network is? We should start a poll. You can give some answers, and it will be clear from Dan's section of the presentation what sort of ballpark numbers we're talking about in terms of the number of kilometers. So obviously, to calculate this number, we don't want to spy on everyone and manually calculate all the trips that are taken on the motorways. So how can we do this without tracking every single trip? What we want to track is a number we called VKT, which stands for vehicle kilometers traveled. And what I'm mostly talking about in this presentation is one way that we estimate this number with machine learning. And the data we get out of this system can be used for other things as well. So to do this, we first need to divide the network into small road segments, which are small sections of the road. And for each of those small segments, we want to find out the number of vehicles that pass through that small section. So how do you do that? So to calculate VKT, we can, if we have the length of the segment and the number of vehicles passing through it, we can basically multiply those numbers to get the total number of kilometers traveled by all the vehicles in that segment. And we sum it up across all the segments on the motorway for every hour of the day. And we can get a rough number of the total kilometers traveled by everybody. But obviously doing this is not as easy as it sounds. The first thing we need is data. So for this project, we use two main types of data, but in the future, we can use things like the computer vision stuff that Sam was talking about. But the main types of data we use is the inductive loop data, which are basically metal wires underneath the ground, as Sam probably mentioned. These give relatively accurate count data of the number of vehicles passing over them. The other type of data we have access to is GPS probe data. These comes from various fleets of taxis, trucks, as well as some GPS devices on the car, in cars. And no data is perfect. So we definitely have challenges in both of these data sources. For one, we don't have loop detector data everywhere on the network. And for places we don't have loop detector data, we don't actually know how many vehicles were in those road segments. The other problem with loop detector data is they can break for a variety of reasons. And there can be gaps in the data because it went offline, one lane stopped working, or there's a wide range of other random things that can happen in the real world. And with GPS probe data, we get good speed data, but since we obviously don't have GPS devices on all the cars, or like we don't get data, we can't tell how many cars were in the particular section of the road. So any ideas how we can use machine learning to solve some of these problems? Just as a reminder, we basically want to estimate the traffic volumes or the traffic parameters for every hour of every day for every segment. So one way you can think of doing that is we can fill in missing detector data with machine learning. Imagine one of the detectors stopped working, maybe the red one in the image here. One thing we can do is we can use all the available data from all the other detectors to estimate the volume at this location. Essentially, we're trying to exploit the patterns that we have seen in the data to predict what the data would be when it's missing. A drawback of this method is that it may not be accurate when there is an incident in the network, for example. But it is useful to get a general idea of the state of the network on a day, like working out demands during COVID-19, for example. So this is not what we use in our main system. What we use, so we basically use the other loop detectors to estimate the missing data. So loop data is not the only source of data we have as well. We also have this GPS probe data. So is there any way we can use this GPS data to estimate volumes? In this case, in the map, assume the circles are the loop detector data. This is just for illustration purposes. This is New York, not Auckland. Imagine the circles are basically where we have loop detectors, and the GPS loop, the GPS traces, you can sort of illustrate it in the traces in the image. So what we can do is create a machine learning model where for each of those loop detector locations, we can use the GPS probe data as input, and we can set the output to be the volume of that loop. So we train this supervised machine learning model, and when detectors are generating good data, we can train this model for only when the detectors are generating good data, but we can estimate volumes even in the case where that detectors are not working. I won't go into the nitty-gritty of how we do this exactly because I don't think we have time. But we essentially do what we do is we combine the GPS probe data with other easily available sources of data, like the characteristics of the road, the place, and the day, to give us an indication of traffic volumes. And we make this function, this machine learning model, quite generalizable, so we can estimate traffic for a wide variety of places that we actually don't have detectors in as well. We do a few more things under the hood to get speed and volume estimates for all segments on the motorway for every hour of every day. And with that, we can essentially have what we believe is a good digital representation of what is actually happening in the real world. And with this digital representation of reality, what we can do a lot of useful things to optimize the network and also help other people. I'll talk about one. By the way, all these projects, I'm not the only one involved. There's a huge team, and there's multiple people involved. And I'll talk about one of the optimizations that we're doing on the Auckland Harbour Bridge. And And also another disclaimer, these systems may not always be connected to each other, but this sort of idea should give a general idea of what sort of optimizations we do on the network. So for every day, more than 170,000 vehicles use the Harbour Bridge, and is one of the most important parts of Auckland's motorway network. Anyone know how many lanes are on the bridge? There's actually 8. Any ideas on how many northbound? Is it 4 in each direction, 4 lanes in each direction, or is it 5 lanes southbound, 3 lanes northbound? Well, that actually, you can see on the picture, it's actually 4 each direction in the picture, but you also see the concrete barrier in the middle. That barrier can actually be moved in either direction. So you can have 3 lanes or 5-3, or there's various different configurations. For example, in the morning, when everybody wants to get to the CBD from the North Shore, we actually have 5 lanes going southbound into the city. And during the afternoon peak, when everybody wants to go from the CBD to the North Shore, we have 5 lanes going northbound and only 3 lanes going southbound. And during the middle, we sort of leave it at a 4-4 configuration. And the times that this move happens from the 3-5 lane configuration to 4-4 is generally based on gut feeling of what we know. But we want to make this more data driven, so we can optimize. For example, sometimes, so for example, in the afternoon, if the afternoon traffic is building up faster than normal, we can move the barrier machine at 2 p.m. instead of 3 p.m., for example. And sometimes we don't need to move the lanes at all. In this example, you can see our dashboard where during alert level 3 in Auckland, for example, we actually didn't need to change the barrier machine at all because demand was below the 4-lane capacity in both directions. That can save time and effort by a bunch of people. So this is one way machine learning can be used here is to forecast traffic on the bridge ahead of time, and we can use this this predicted traffic to basically decide on the time. Because right now it is there is a man in the middle, and because of the unpredictability of COVID and things, it has impacted a bit, but we're integrating these forecasts into the optimizing the time as well. Speaking of impacts on COVID, I'll now pass it along to Dan, who'll talk about how COVID has impacted traffic on our motorways.
Thank you very much, Ravindu. Hello, everyone. So I'm going to talk about the impacts of COVID on our traffic network. So Ravindu has already covered, basically the theory, and I'm going to cover the application on a larger scale. So the Auckland Harbour Bridge is an example of a single key infrastructure of Auckland, which there are standard move times, and we try to optimize it. But on an entire network, we have much more missing data across the entire network. So picking COVID because everyone's very familiar. It's something that we've experienced in the past 2 years. And this is a picture of the first day of alert level 4, the first morning of alert level 4, which the network was basically completely empty. In terms of its application, right? First, we have to start with a question. The problem that we are trying to solve and this new technology is trying to assist with. So, are there less cars using the motorway? Right? Is there possibility for a change in the BAU process of physical works? When is demand back to normal? How much effort is required to keep the network at its state running as normal? These are the questions that you might have wondered, and without the support of actual data, when you look at the first questions, are there less cars using the motorway? The answer may be yes, based on feeling. I feel the network is a bit lighter than what I would have experienced in 2019. But by how much? As decision makers, you need data to support and back up your claim. There's also possibility of extending the maintenance window over the night, which potentially will make these maintenance work more efficient. So to answer these questions, we'll have to look at the data. Here are two snapshots of the VKT. So looking at the poll done earlier, majority of us got it right. And on a typical weekday, the VKT is around 12.5 to maybe 13.514 million on a busy day. And for weekends, that's about 8 to 9 million. So whoever answered 5 million to 20 million, give yourself a pat on the back. On the top image is 2021, where we still had the old alert level system where we had alert levels 1, 2, 3, 4. And here highlighted in red, you could see when we were in the second alert level 4, the demand was down about 70 to 75%. So yes, the network is definitely much lighter. You won't see any congestions. But from that, you are also able to estimate how many travels are actually essential movements as they would need to travel. And then at alert level 3, which is towards the right on the top graph, you see the demand reductions about 35%. So we're still well below the capacity of the network, and you still probably won't see any or experience any congestion. Moving forward, coming to this year, 2020, on the bottom graph, you see that demand is kind of back to normal. But you may wonder, with so many offices and businesses still working flexibly, allowing remote working from home, how is it possible that it's, going back to normal, or the demand on the network is going back to normal? So right now we're still investigating this issue, but some potential causes may be a mode shift. So less people take the train, public transport, and decide to use cars. When we look at it in terms of the demand, when we look at it in a bit more detail, another pattern we have observed is that the morning and evening peaks are not as concentrated in terms of demand, as you can see here. So this is just a typical week from May this year, which was quite recent. And as you can see, the morning peak and afternoon peak demands are less than the typical day range, which is highlighted in gray, whereas the interpeak is on the lower end of the typical day range, which kind of means that with work being much more flexible, you don't have to arrive in the office at 8 sharp. And potentially you could have half a day with meetings in the office and then the other half of the day working from home. So your commute has much more flexibility, and the interpeak would cause less delays, which is why people would potentially choose to travel more during the interpeak and less during the AM and PM peaks. So that about covers the application on a network-wide scale. And I'll pass back to Sam.
Cool, thanks Ravindu and Dan. So that's all from us for today. If you want to learn more, or you think you might be able to apply some of this technology to your industry or business, feel free to get in touch and we'll see what we can do. We're also looking to expand our team, so if this looks like an area you want to work in, also get in touch. We've got some time for questions now. So if anyone's got any questions, feel free to, I think, drop them in the chat, I believe. Thank you very much.
There are some there, Sam. So I can, in order of priorities, let's start with Tim's question. How do you verify reliability of the data you use, including the data generated from machine learning?
Cool. I can take that for the volume estimation type stuff. So we do the traditional train test split, but in terms of verifying the data, there is obviously a big data cleaning step before we use it in the machine learning models, just to check for outliers and obvious mistakes. But and also the other thing we do is with the volume estimation stuff, we can actually use we can basically train the model without using just using a subset of the data. For example, we can verify, like we have data for a location, but we actually don't use that in our model. We train the model and then we actually check if the actual measured data actually corresponds to the real world data. So there's a bunch of things we do around that, and also we do have dashboards to monitor sort of when data is sort of missing and things as well.
Thanks, Ravinder. Another question, how do you cover off concerns about privacy with these technologies?
I can cover that a bit. So with things like GPS data and Bluetooth, these are typically purchased from third-party suppliers, so WSP isn't collecting that themselves, but privacy is definitely a big concern for these technologies. So the data is aggregated and anonymized, so the data that comes to us doesn't have any personally identifying features. Similarly for the computer vision stuff, the solution I showed there didn't collect any number plates or anything like that, and there's also controls on where those video feeds come from and who can access them as well.
Thanks, Sam. Another question, how transferable are the methods learnt in Auckland to other parts of the country and the larger motorway network?
I could probably talk about that. Right, so it's definitely transferable and applicable in other cities as well as the wider network. In terms of these technologies, it's heavily dependent on data. So with more ways to collect data, for example, using cameras rather than loops, it is definitely more possible than before that we can fill in larger gaps in the network, especially like the rural network where there's very few detectors. Yeah, so definitely transferable.
Thanks, Dan. More questions, lots coming through. How do you ensure policymakers, i.e. people making big infrastructure decisions, take a data-driven approach? Big question.
There might be best.
Yeah, I could try. This is a big one. We try our best, right? We try our best. So, when you do the work and you deliver basically the client's confidence in your product or your technology will be based on the outcomes and compared to what actually happened, right? So if you predict something and you forecast something and it turned out, it was worse than BAU, then you kind of lose that confidence in the technology. So I definitely think we try our best and to deliver good work, and for example, policymakers to have trust in the technology to potentially influence.
Thanks, Dan. Do you have access to comparative data? So other international cities, how are other cities managing their traffic flows?
Okay, I'll take this one as well. We're definitely looking at this, and at the ASM we are constantly looking out for other cities in terms of how they manage their motorway networks and the international best practice.
What is accepted accuracy percentage when calculating VKT? So what is the accepted accuracy percentage when calculating VKT?
I can have a go at that. So the problem with the VKT metric is there is no like ground truth data. So it's not easy to have like a very, what we do in this case is basically we have multiple ways of estimating it. So one way is we can use traffic flow models, and there's another MARS system, which is I don't remember what it stands for. There are multiple systems that we sort of correlate and make sure that all of them are giving similar answers. If Dan wants to add anything else. CO2 emissions is something that we currently indirectly track using the VKT metric, and in the future with computer vision stuff, it may be possible to give a more granular view of that as well. But yeah.
Great, thank you. What's the accuracy of computer vision at night versus during the day?
I'm not sure of the details of our system. I haven't been involved in the development, but I do know that you can train it for certain circumstances. So the training data basically needs to cover the various different situations it might encounter, including nighttime, bad weather, and things like that. So by training it across a range of different situations, you can ensure that you get good accuracy in all the cases. Nighttime does give you some challenges. You might not be able to see what type of vehicle it is as easily as at daytime. But this relates to data loss due to lack of visibility as well. So to that question, I'd say we position cameras to give the best visibility, but also I think we can report back confidence levels. So if we think there's an issue with how it's being reported, we can report back a lower confidence and maybe rely on other data sources to give a better picture of what's going on.
Right. I think we're in our last kind of 3 minutes. So how do you deal with data loss due to lack of visibility of cameras due to obstacles or other reasons?
That's what I just covered in the last one, I think.
Yeah. How do you plan on processing the vast amounts of camera data?
Yeah, it's a good question. So typically we would be accessing camera sources from our network operators, and they generally do the data management. But yeah, so it will depend on a case-by-case basis, but we don't ourselves intend on storing large amounts of data. It's more tapping into existing data resources, basically.
Great. What use is made of Google location services for validating predictions?
Dan, do you want to go at it? But we do sometimes double check the travel times with Google, but generally Dan might have a better idea if there's a process.
I could try. I'm not the best person, but so Google, we've dealt with this data source previously, and from our understanding, it's kind of like a black box, which we don't know what exactly is going on. So rather than Google, we use TomTom a bit more often.
But yeah, Google doesn't give us a lot of GPS data or like any, just what is available to the public is what we have.
Thank you. Do you use a supercomputer to crunch the vast amounts of data? Great question.
No, we don't. We use regular computers with GPUs and things. So, but we do need a lot of space to store the data as well.
Great. Thanks, everyone. I think that's all our questions for today. I just want to say a big thank you to Sam, Ravinder, and Dan for sharing all this great innovation that you and your team have done. Everyone, please also join us on our later sessions today. As mentioned in the chat, there is a link to the other sessions as well. So thank you for your time, everyone, and have a great day.